Alright guys, welcome to vodcast 4.1. We're going to talk about the history of atomic structure, and there's most of this chapter has a lot of notes and definitions and stuff like that. Some of this will be included in the notes that I'm going to hand out to you, so you don't have to write quite as much, but you still need to follow along pretty closely to make sure that you catch all the points, particularly when we get to the experiments that talk about the development of atomic structure here in a little bit. Okay, so atomic structure basically starts back around 400 BC or so with a Greek philosopher named Democritus. And of course, there were tons of Greek philosophers. You probably heard of Plato and Aristotle and all those guys. And Democritus' big idea was that he basically is the first guy that uses the word atoms. It's the Greek word atomos. And his idea was that matter was made up of empty space and then of atoms, which were basically little tiny particles, is what he called them. Now, this wasn't very popular at the time because the sort of standard Greek idea of matter was that of the four elements. Okay, so you had air, fire, earth, and water, and that those blended together formed all of the other things that make up the world. And additionally, the Greeks sort of thought that matter was sort of this big, continuous, long thing, that it wasn't like these individual, discrete pieces. Okay, so as we move a little bit more into modern times, the first big name that pops up is that of John Dalton. He was an English school teacher who did a lot of science stuff on the side, and he's the first guy that really comes up with what we would start to categorize as modern atomic theory. And so he's got 5 main points to his theory. These are going to be in your notes partially, but you need to copy down the parts that aren't there and make sure that you get those in there. So the first point is that he basically said that atoms are made of, or elements are made of extremely small particles called atoms. Okay, that makes pretty good sense. Nothing really too terribly hard to gather about that. So that's point one. Elements are made of extremely small particles called atoms. His second point is that atoms of a different element or of a given element are identical, and atoms of different elements are different from one another. Now that seems to make pretty good sense, but the idea was that every gold atom is the same as every other gold atom, and that gold atoms are different from silver atoms. That oxygen atoms are all the same, but they're different from nitrogen atoms. And we'll see a little bit later on that that's partially true and partially not true. Part of the atom for a given element is always the same, and then part of it can differ a little bit. And we'll talk about that in tomorrow's podcast. So Dalton's third point is that atoms are indestructible and indivisible. And if you've never known what the word indivisible means every time you say it in the pledge every day, indivisible basically means that you can't divide something, that you can't break it down further into pieces. So according to Dalton, atoms were basically just these sort of small hard spheres, like we talked about in kinetic theory, that there was nothing in them. Like if you could break it open, which he said you couldn't, but if you could break it open, that there's nothing really inside. It is the smallest thing possible. His fourth point, and this one we'll see later on as an actual chemical law, but Dalton says that atoms of elements combine in whole number ratios to form compounds. What that whole number ratio thing means is that you can't have like half an atom forming a compound or 3/4 of an atom or something. It has to be a whole atom. So you get one atom and another atom, or 2 or 3 atoms, but it has to be whole numbers, that there's no fractions or decimals in terms of the numbers of atoms. And Dalton's last point, point 5, is that chemical reactions basically are involving these atoms that he came up with and how they switch around and how they rearrange with one another. Okay, and that was pretty important because prior to that, the guys that were sort of chemists before that, the alchemists, they had all these ways that they thought stuff worked, and they thought maybe there was magic involved and maybe there were scientific principles, but no one had an idea of what was actually happening when a chemical reaction occurred. You know, when you added acid to base and you got this big flare-up of gases, and then you got water at the end, what was happening? Dalton is the first guy that really says, hey, what's happening is that the atoms are moving from one place to another. They're getting rearranged, their bonds are changing, all of those sorts of things. Okay, so what does Dalton's atom look like? Well, essentially, Dalton's atom is like the simplest of all of the atoms that we're going to talk about today. And this is basically true of Democritus' atom as well. I mean, that's basically it. According to Dalton, I mean, an atom is just a small sphere. Okay, it's just a ball, and there's nothing inside of it. You can't break it open. Remember, they're indestructible and indivisible. Can't break them apart. Okay, but as scientists started to do a little bit further work, what they discovered is that that wasn't entirely true, that you could start to break those things down. And the first big experiment where we break these things down, just like the little diagram animation here now, is Thomson's cathode ray tube experiment. And so let me real briefly explain what's going on here. This is an evacuated tube, so basically I think it's, if I remember correctly, it's called a Crookes tube. And it's basically a glass tube, and you've got a wire in here that basically is electrified, so that it's generating this beam here. The blue beam here, is called a cathode ray. Okay, and they had been able to generate the cathode ray beams for a while, but they weren't really sure what they were, and so Thomson's sort of experimenting to try to figure out what it is. And what the animation here is showing is that under normal conditions, okay, the beam just goes straight through. Okay, it doesn't bend at all. It just goes from one side of the tube to the other. But what Thomson did, and what really made the experiment here, is that he puts these two magnetic plates here, and that's when you see when the little plus and minus turn on here. That's basically them turning the magnet on. And when the magnet happened, what you see happening is that this beam goes away from the negative side. It goes toward the positive side, and it goes away from the negative side. So it's going to slope down this way. Okay, now that's really super important, because one of the things that we know about electricity or about magnetism is that like charges repel. And so the fact that the beam was repelled by the negative side of the magnet meant that the beam itself had a negative charge. Okay, so this was a really big deal. So here's basically what this experiment proved. First off, that there were smaller particles that made up atoms, because the cathode rays had mass, okay, but they were not the mass of the smallest atom. The smallest atom is a hydrogen atom. There's nothing smaller than that as far as atom sizes, but the mass of these particles was really, really, really small. It was later proven by some other guys, but this mass was really small, and so therefore there had to be a particle that was actually smaller than the atom. So this sort of disproved Dalton's idea that you couldn't break the atom apart. And perhaps just as important is that one of the particles, okay, because at this point they don't know that there are any other particles, they know that there's at least this particle. One of these particles has a negative charge, okay. Now we're going to know that, and you know that from your previous science classes, as the electron, and we'll get back to that in another lesson here in a little bit. So particles have a negative charge, and we can break the atom up. Now, Thomson and his experimenters, they knew that the atom is overall neutral, though. So if there's a negative charge, there must be a positive charge. So this leads Thomson to come up with what is called the plum pudding model. And basically the idea here is, and I don't like the idea of plum pudding model, I prefer to call it the chocolate chip cookie model. So if you think of a chocolate chip cookie, you've got a cookie part, like the batter that gets cooked, and then you've got all these little chocolate chips dispersed throughout it. So in the plum pudding model, or the chocolate chip cookie model, the electrons are the chocolate chips, and the cookie itself is this big positive mass. And so this is what Thomson thought an atom looked like, that it was a big positive mass, and that there was these little electrons embedded all throughout it. Okay, now according to Thomson's theory, this positive space really didn't take up much space. It was kind of like, it was almost empty space, and this is going to be further borne out to some degree by the next experimenter, who's a guy named Ernest Rutherford. Rutherford does this thing here. You see this really complicated looking diagram. Rutherford does this famous experiment called the gold foil experiment. And again, according to Thomson's plum pudding model, everything that should happen here is going to go through. So what do we mean? Okay, let me briefly break this down. If you really want to see a great video of this, if you go to YouTube, there's the link right here. You can go to YouTube and jump and watch that video. Or if you've got a cell phone or something like that with you with a scanner, you can scan this QR code and you'll jump right there and it'll show you how it works. But basically, this is the gold foil experiment. Rutherford's team, Geiger and Marsden, Geiger of the Geiger counter, who's one of Rutherford's assistants, they have this block here that's firing alpha particles. What alpha particles are doesn't really matter that much, except that we know that they're positively charged. It's basically a helium nucleus, 2 neutrons, 2 protons. That's what they're firing. They don't know that at the time. They just know they're alpha particles. So they're firing a beam at a little thin tiny piece of gold foil, and it is just what it sounds like. Think of aluminum foil, except it's made out of gold instead of aluminum. Now according to the plum pudding model, when they fired this beam, everything basically should have gone through, because the positive charge is just sort of this nebulous spread out mass, almost all empty space. And what actually happened though when they fired it is that some of the particles got deflected, and in fact some of them actually got deflected almost completely backwards. And this big famous quote that they make at the time is that it was as though they had fired a mortar shell at a piece of tissue paper, and the mortar shell came back. That's how shocked they were that anything happened. And what actually did happen is that the alpha particles, which are positively charged, were hitting a dense positively charged center in the atom. Okay, most of them went through, like over 99%, but some of them hit this center part of the atom. Now we know that the center part today is called the nucleus. Okay, the nucleus in an atom is where all the positive charge resides, and we'll get back to that in the next lesson. But just remember, this is what Rutherford's experiment shows: is that instead of it being this spread out positive charge of Thomson's model, that all the positive charge is in one space in the middle, okay, which is the nucleus. Okay, and so this is another sort of showing Rutherford's model compared to Thomson's model. The electrons are still sort of just out here or wherever, and these are the alpha particles going through, and we see some of them, bam, as they run into the nucleus, they get deflected in different directions. Some of them get deflected back, some of them just get their course altered. Most of them still make it through, okay, but a few run into that really dense nucleus. Okay, and real quick, if we just jump back real quick so you can see the difference, Thomson's plum pudding model, the positive charge is everywhere basically. Okay, cookie of the chocolate chip cookie. And then in Rutherford's model, the nucleus is all right here, right in the center. Okay, all the positive charge is right there in the middle. Okay, so the next model is what we call the Bohr model, and this is the one that you probably saw a lot in elementary school or in middle school. Is basically this: that you've got a center where the nucleus is, and then around that you have like these rings where the electrons are. They're often called orbits or orbitals or energy levels. And Niels Bohr comes up with this, and this is often what's called the planetary model, because the idea is that the electrons are circling around the nucleus in the same way that planets orbit the sun. So like the sun, and then this would be Mercury, Venus, and Earth. Same sort of deal here would apply to atoms, that there's a nucleus in the middle, okay, just like the sun, and then the electrons are orbiting in these different energy levels around that. Now Bohr was partially correct. He was correct in the idea that there are some energy levels, but his model was only really applied to hydrogen, and as things got more and more complicated, they had to come up with a more complicated model. Now the good news is we're not really going to talk, we're not getting into the big heavy math, because to be honest, I don't even know all the big heavy math in the modern model. The modern model is what's called the quantum mechanical model, and if that sounds really complicated, it is. But here's the general gist of it. You've got a nucleus here, and these are the neutrons and protons in the nucleus. And then you see these like fuzzy areas here. You see that they're called electron energy levels, much like in the Bohr model. But they're all sort of fuzzy and diffuse. That's what the quantum mechanical model says. Basically, it says that we can't absolutely know where the electron is, but we can mathematically prove that there's a high probability that it's in a certain place. And they're not really in these necessarily circular orbits, but rather that they're in all of these different shapes. And when we do electron configurations in the next unit, we'll talk more about those spaces. Okay, so that's a brief history of the atom. I know that's a lot of information. Make sure that you got everything possible down in your notes. Particularly make sure that you know those 5 points of Dalton's model. And then we're going to do a little activity today where you're going to need to draw each of the models. So if you didn't look at the pictures really hard, you might want to rewind the video real quick and go back and make sure that you know what each of the pictures look like, so you can draw each model and what's different from each step to each step. All right? Thanks, guys.